Hi guys, week 6. We're going to talk about Bayesian classification this week. I hope you like my background, by the way, and there's brownie points if you can tell me where it's from. What is this background that I'm currently on? Okay, so we've looked at two classifiers so far, k-nearest neighbor and decision trees, and we compared the two of them. I had you do that in an assignment. So k-nearest neighbor takes a very kind of simple approach to classification. There's no real training phase. It just remembers all the training data and then pops out new answers to unseen examples by seeing how close they are in a feature space to known examples. Decision trees is a much more AI-y, artificial intelligence-y kind of approach. In fact, it smacks of good old, what they used to call, I don't know if they still do, good old-fashioned AI. So when neural networks first came along, there was huge debates within the computer science community and also within the cognitive science and cognitive psychology community and the philosophical community, philosophers who are interested in philosophy of mind, about symbolic versus connectionist models of mind. And just traditional AI, symbolic and rule-based AI, versus neural networks. Excuse me. So decision trees is one that's very much rooted in good. It looks very much like good old-fashioned AI. You're doing a search through a feature space. You're creating rules that are personified as decision trees and so on. I think that debate, which was raging when I was studying cognitive science and machine learning, has pretty much died down now. People see a place for all of these techniques, and people aren't so upset about it anymore. But in any case, naive Bayes is something completely different. This one comes out of pure statistics and mathematics. It's a technique that was derived, so it's kind of less artificial intelligence looking in terms of the way artificial intelligence usually is considered, and much more mathematical. So what I'm going to do, these videos might be a little shorter, but what I'm going to do is go through the Bayes rule, which so Bayes was a guy, by the way, blanking on the first name right now, but Bayes was a mathematician who developed Bayes' rule, and that's the rule, the mathematical equation that a naive Bayesian classifier is based on. And we'll talk about why naive in the next video. But in this video, I just want to explain Bayes' rule to you because I have a feeling you haven't seen it before. I know you've done some probability mathematics before, some mathematics of probability, but you probably haven't done conditional probabilities, and you probably haven't seen Bayes' rule. That's been the case in previous years anyway. So we're going to go over it. And then in the next video, I'll explain how the Bayesian classifier actually does what it does. Now, we're going to get a bit mathy here, but we're not. It's not really theory. I'm giving you the math. I'm explaining the math to you so that you understand how the classifier works. And I think there's no better way to show that you understand it than to show that you could crunch through a few numbers and apply the theory to come up with a result, come up with a classification. So that's what we're aiming at here. The actual code this week, the assignment 2A that I'll introduce probably in the next video, or maybe I'll make a third one for it, is pretty minimal. There's not much to do in the code. Naive Bayes doesn't really have any parameters that you can tune. So it's really just a question of taking naive Bayes and using that on probably the same data set that you did on decision trees. So that part is kind of minimal, and there's more emphasis on the mathematics of it. It's not theory, though, really. I mean, if this was really a theory course, we would probably try to derive and prove Bayes' rule, and then maybe even derive and prove some results about Gaussian distributions, normal distributions, and so on. We'd be trying to prove things and justify things. All I'm going to do is demonstrate to you what the Bayes' rule is and why it works, and then show you how it's used. We're going to do that by plugging in numbers. I'm also I'm going to leave you guys with some exercises to show that to sort of develop your understanding, and I won't take those up here. I'm going to debrief them in the live class. So in the live class, we'll take up the examples. I have 2 exercises, one in this video, one in the next video, and really those exercises are mostly preparing you for the test, which will focus on these more conceptual topics. So let's take a look at the handout for naive Bayes. Here it is. And on the first page, I'm just let me explain to you how this works. So let's say you're trying to categorize, I don't know, I was just emailing a student about a scam email database. So we have two examples of two classes. One class, it represents scam emails, emails that are trying to trick you or get you to reveal personal information about yourself. And on the other hand, we have a big set of non-scam emails, ordinary emails, or perhaps advertising emails that are not considered scams. And these emails have been boiled down to a feature string of numbers. Bayesian classification has to work on numeric features. It can't cope with like nominal features and things like that. It has to be numeric. And then how the decision tree, for example, would approach it is it would come up with some rules. Would say, if this word appears this many times or more, then go this way in the tree, and then it'll check it to maybe a different word. And if that word appears less than 5 times, go this way, and it's a scam. The Bayesian classifier comes up with probabilities. So it forms a theory of what would categorize something as scam versus non-scam, and that theory is based on probabilities. And then its output is for each of the classes it knows about, it tells you the probability that it thinks that the new thing belongs in that class. And then you do that for all your classes that you know about, and the highest one wins. So if it comes out 0.8, because probabilities are always between 0 and 1, so if it comes out 0.8 probability for scam, 0.2 probability for not scam, then you go with scam. So it's kind of neat too, because it sort of automatically generates a confidence. If it comes out 0.56 versus 0.4, then it's maybe less confident than if it comes out with 0.9 versus 0.1. So here's a simple example. So it says, suppose that a classification task is to predict, based on the weather, what someone will do on their day off. So they might play tennis, they might play badminton, or they might watch TV. I don't know what kind of person this is, but those are the 3 things that they might do. The features are overview, which is, so this is based on the weather, sunny, cloudy, rainy, and temperature, which can be hot, warm, cool, or cold. So this isn't the kind of data that we would really use for our naive Bayes classifier, but it's good for illustrating a point. So there are 2 features, overview and temperature, and I'm expressing probabilities this way. So what we want to know, given that today it's cloudy and cool, we want to know the conditional probability. So P is for probability, and in here this is where you might not have seen this bar before, this straight line up and down bar. So the class tennis, what is the probability that this example fits, that this person will play tennis based on the fact that it's cloudy and cool? So given that it's cloudy and cool, given that condition, what's the probability that they'll play tennis? Given that and then secondly, you want to know what's the probability that they'll play badminton, given that it's cloudy and cool, and what's the probability that they'll watch TV, given that it's cloudy and cool. Okay, so these are conditional probabilities. Here's the basic form of it. The probability, this means the probability of A occurring, given that B is occurring. So the probability that Trump will win the election, given that the Black Lives Matter movement is much more ascendant than it was before, something like that. So these are conditional probabilities. And let's say that the following is true. So the probability for tennis is 0.3, given that it's cloudy and cool, badminton 0.8, TV 0.5. So looks like badminton, I guess, because it's an indoor sport. I don't know. So that's the most likely thing that will happen. But again, you can read this like a little bit of confidence. It's maybe not super confident because it came out with a 0.5. There's a kind of a coin flip probability that it's cloudy, that they'll watch TV. Okay, so that's what the output's going to look like. Now in sklearn, you can get these probabilities, or you can just get it to predict a class. But that's how it's doing it. It's working out these conditional probabilities, one for each class, based on the features that you gave it, saying what is the probability of class A given these feature values, what is the probability of class B given these feature values, and so on. And then it finds the highest one and pops that out as its classification. So a few key characteristics. So there's a training phase. There isn't always a training phase like K and N, but we construct a theory. It's fast. Both training and categorization are fast. Bayesian classifiers, naive Bayesian classifiers, often can do well with a very small amount of training data. And sometimes they don't, but sometimes they do really well. And that seems to happen a lot. So more so than KNN, than decision trees. There's not many learning parameters to tweak, if any at all. And you can read the output as a level of confidence kind of naturally. There are ways to tweak decision trees and KNN so that they come up with estimates of confidence or probability as well. But this is baked right into the system. Okay, so that's what we're doing. Now, it turns out that what we want is this. We want the probability of each class given the set of features, the example that we've got. So the probability of, I don't know why it's doing that, that's interesting. The probability of the class given the example. But it turns out that it's often quite difficult to estimate that in practice. It's much easier to estimate this in practice. That is the probability, if this was a cat, what is the probability that we would have gotten this set of features if it was a cat picture? What is the probability that we would have gotten this set of features given that it's a dog picture, and so on? Turns out that in practice, and we'll show why in a second, it's a lot easier to estimate this than to estimate this directly. And but luckily we've got this formula, this Bayes rule formula that relates those two quantities. So if we can estimate this, we can convert it to the thing that we want, which is this. And we do it by taking that estimate, multiplying it by the overall probability of the class. So that's, what are we looking at there? We're looking at, if you've got dog and cat pictures, we may know that people prefer cat pictures. So if you just take a picture without looking at it and say, is it a dog or a cat? Maybe there's a 60% prior probability that it's going to be a cat picture without even looking at it. So that's that probability. So you can estimate that just based on the number of class pictures in your, the number of cat pictures in your set versus the number of dog pictures. And then the overall probability of getting that set of features. So what we do is we're estimating feature probabilities. So what's the probability of those features given the class? And what's the overall probability in the whole set of getting those features? Right? Okay. So let's work through an example. I don't know if that's fully explaining it, but if we work through an example, I think it'll make it a little bit easier. So let's look at the weather data over here. Okay, this is a very simplified version of what I just showed you. This is just representing whether or not someone will play tennis. So there's only two classes, yes and no, and there's only one feature to make it super simple so that we can estimate probabilities ourselves. There's three values for the weather: sunny, overcast, and rainy. And we want to know the probability that they will play tennis, that the class will be yes, given the feature value sunny. So given that the weather is sunny. And we can directly estimate that. So I'm going to try and do this. We'll see how well this works over here in a whiteboard. I'm using an actual pen here that I acquired for this purpose. So we want to know, whoops, I got to get into my pen first. We want to know the probability of yes, given that it's sunny. Okay. Now, because deliberately this data is simple enough that we can directly estimate it. So probability that's yes, given that it's sunny. So that means we just look at the sunny column here. So how many sunnies do we have? 1, 2, 3, 4, 5. There's 5 examples in our data set where it's sunny. So that's the only ones we're looking at, given that it's sunny. How many of those are a yes? Not that one. That one is, that one is, that one is. So equals what? Equals 3 out of 5, just based on the direct estimate. Okay, so this is deliberately chosen to be simple enough that we can do that. Sorry if that's kind of hard to read. All right, but we want to use the Bayes rule to do this. We want to do it a different way. So let me just, so we know that the advantage of this is we know the answer that we're looking for is 3 out of 5. What I'm going to demonstrate to you now is how to do this just using the Bayes rule. So using Bayes rule, we know that the probability of yes, given that it's sunny, is equal to the probability that it's sunny, given that it's a yes, times the probability that it is a yes over the probability that it is sunny. Okay? So we have to estimate all of these different properties. So let's start with the probability of a yes. So the probability of a yes, so we estimate this just by looking through all the data, and we count the number of data points. I believe there are 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, there's 14 data points. How many of them are yeses? That's going to be our estimate. So I think there are 9 yeses. 1, 2, 2, 3, 4, 5, 6, 7, 8, 9. 9 yeses. Okay? So we're going to go, that's 9 over 14. That's the probability. We could work that out to a decimal, but it's easier to just leave it like that for now. So the probability of a yes is 9 over 14. What's the probability that it's sunny? So the probability that it's sunny, again, there's 14 examples, and we already worked out there's 5 of them that are sunny. So these are estimates. Now, when you're doing this kind of probability estimate from real-world data, so this is a common way of doing things. If you don't know what's the probability in advance that it's going to be a sunny day, given any day of the year, you could look back over historical weather data. You'd probably find tens of thousands of days or thousands of days, and then just add up the numbers that are sunny and divide by the number of days, and that's your estimate for the probability of a sunny day, in any particular part of the world. Is it going to be the exact probability, the exact correct probability? Probably not, but the more data you have, the closer it's going to approach the real number. So having a lot of data is usually a lot better, although it does turn out that naive Bayes can do well with small amounts of data, as I said. Naive Bayes kind of surprises us in a lot of ways. It's surprising that it works as well as it does. We'll explain why a little bit more later on. But that's one of the surprises, is that with small amounts of data, it can actually form a theory that actually works quite well in many cases. So we have 2 of the quantities, the probability of a yes and the probability of a sunny day. The other probability, which we're going to estimate directly from the data, is the probability of a sunny day given that it's a yes. Sunny day. Okay, that's an S. So give this probability of a sunny day given that it's a yes. So we are only looking at the yes days. 1, 2, 3, 4, 5, 6, 7, 8, 9. We're just looking at those 9 yes days. So that's going to be a 9 over. I'm sorry. That's the denominator. So there's 9 total days we're looking at. Given that, yes, sorry, I just confused myself for a second. It's easy to get confused here. So we're looking at the days where it's a yes. So there's 9 possible days where it's a yes. How many of those were sunny? 1, 2, 3. Looks like. I see 3 that were sunny. So 3 over 9. So now what we do is we just plug these numbers into that formula up above. So this is equal to, I'll just keep going in red here, 3 over 9 times the probability of a yes, which is 9 over 14, divided by the probability of sunny, which is 5 over 14. And what's kind of nice about this is you can see let's use blue just for fun. These denominators cancel out when you're multiplying like this. Oh, I should have been using a smaller brush stroke. That's my mistake. I'll fix that next time I do this. Those denominators cancel out, so it becomes 3 over 14 over 5 over 14 over 5 over 14, which is equal to 3 over 14, if you remember your fractions, times 14 over 5. When you divide by a fraction, you flip the denominator and the numerator and the denominator and multiply. So you get the reciprocal, and then the 14s cancel out, and it's 3 over 5. Sorry about the fractions. I know a lot of people don't like doing fraction arithmetic, and sorry about my messy whiteboard. I'll get better at this as I use these whiteboards. But this is what we were looking for, is the probability of yes, given that it's sunny, which we already knew was 3 over 5, because this data is so simple, we can estimate it directly from the table. Like there's 5 sunny days, 1, 2, here they are. I'll mark them with blue. And 3 of those are yeses, 1, 2, 3. So we knew that the answer was already 3/5, but surprisingly, we could get it this way too, by using Bayes' rule. So that's kind of interesting. Now, I haven't proved Bayes' rule here. All I've shown is that it works in this case, but of course it can be proved, and it has been proved, and so we know it always works. This is just one example of that, one illustration of that. So Bayes' rule works. What remains is to show why this is relevant and how it's used in classification. Okay, so we turn this into a classifier, into a naive Bayes classifier, by making one big naive assumption and a second, maybe less naive assumption about the data, which allows us to calculate particularly this quantity here. This quantity here, it allows us to calculate it pretty easily. So that's what we're going to look at next. So let's go back to, not the assignment, to this thing here. So I worked through the same example here. And it looks much neater when I do it here, but I wanted to go over it step by step and show you how it worked. That's why I did it on the whiteboard. And then as an exercise, I say, use the same process to figure out the probability of a yes when it's rainy. So walk through the same, I want you to try this on your own, and we're going to take it up in the live class, but using the same table of data. This will help you make sure that you understand this notation, what probability of A given B means, and how to interpret it. If you're not so good at the fraction arithmetic, you can always just pump these things into your calculator. Just make sure that you get the brackets correct and everything, and check the result that way. But the fractions aren't that hard once you remember how to multiply fractions, because a lot of things cancel out. Okay, so that's it for this video. Next video, we'll take a look at how a naive Bayes classifier actually works, and maybe take a look at some code as well. All right, see you in the next video.